Right, let's move on to question 3, electrostatics question. First question asks you to draw the electric field pattern around sphere P. It's a negatively charged charge, and so we have a symmetrical radial pattern. Remember, the direction of the field lines is determined by the direction in which a small positive point charge would move. That would obviously be attracted towards the negative charge, and so the direction of the field lines are inwards towards the negative charge. Calculate the magnitude and direction of the resultant electric field strength. We've got two charges, P and T. Both of them contribute to the field strength at X. So we're going to have to do two calculations, but notice that the charge of P and the charge of T are the same, 4 times 10 to the minus 9 coulombs. The one's negative, the one's positive. So that simplifies the calculation. We're asked for magnitude and direction, so we need to be careful of that in the answer. Electric field strength E is what we're interested in. Let's start with the effective charge P. At X, there's going to be a certain electric field strength in the direction of P, and we'll label that E for electric field strength, subscript P. Be careful, it's not potential energy, it's electric field due to charge P. Charge T then is positively charged, so it would also create an electric field at X that points in the same direction, because that positive charge now would cause an electric field strength to the left. But because their charges are equal, those electric field strengths will be equal. Alright, let's use the formula. Electric field strength is kq over r squared. K is 9 times 10 to the 9. Q is 4 times 10 to the minus 9. Notice we're taking the magnitude of the charge in this formula. We'll take the direction into account in a moment. R, the distance between point X and the charge, is half a centimeter, and we need to change that to meters, so 0.5 times 10 to the minus 2. Don't forget to square it, and that gives us 1.44 times 10 to the 6 volts per meter to the left. The resultant electric field strength then is simply twice that, because T has the same magnitude charge, and so if we multiply that by 2, it gives us 2.88 times 10 to the 6, either volts per meter or newtons per coulomb. Direction either to the left or towards P. Alright, question 4, the alternating current question. It asks for the RMS current that passes through the 6 ohm resistor. The AC source is 40 volts RMS, but we don't know the voltage over the 6 ohm resistor. So we're going to have to apply Ohm's law. The current that flows through the 6 ohm resistor is the same current that flows through the rest of the circuit. It's the total current. So we're going to have to apply Ohm's law to the whole circuit. So IRMS, that's the total current, which is also the current through the 6 ohm resistor, is VRMS, and we're going to take the total voltage over the total resistance. You're going to be careful there. Total voltage is 40, total resistance is 4 plus the 6, which gives us 40 over 10, or 4 amperes. Alright, then calculate the average power dissipated by the 6 ohm resistor. We're using the formula, average power is I squared R. We've just calculated that current to be 4, so it's 4 squared times that resistor of 6 ohms gives us 96 watts. And then finally, a graph of current versus time to illustrate the flow of the current through the circuit. Remember, this is alternating current. So we've got our y-axis labeled current, our x-axis is labeled time. The AC is generated at 50 hertz, which means that the period of that generator is 1 over the frequency, 1 over 50, or 0.2 seconds. And we're told to draw a trace for 0.2 seconds, which means we'll get 1 cycle in that 0.2 seconds. So we're drawing the classic sinusoidal shape for the current versus time graph of an AC generator. The 1 cycle is generated in 0.02 seconds, and we know that IRMS is 4 amps, and so we just indicate the approximate position of the RMS current.